Hello everyone, I'm Rudra Setuviji, a PhD student at Purdue University working under Professor Pablo Vlahos. Today I'll be presenting our work focused on developing a tracking algorithm for volumetric PTV based on Kalman filters. Volumetric particle tracking velocimetry is an optical flow measurement technique that measures velocity by tracking the motion of neutrally buoyant particles seeded into the flow. The measurement chain involves the application of tracking algorithms to resolve the motion of each tracer particle. Currently employed tracking approaches in volumetric PTV are 1. 3D PTV and 2. Shake the box, known as S2B. From the figures, we understand that 3D PTV follows a pairwise tracking of 3D positions based on nearest neighbor search algorithm. On the other hand, Shake the Box adopts an image matching approach in which tracks are built by comparing projected images of a prediction field and comparing it with the following time frame and by minimizing the overall image residual across cameras. Kalman filters are well known in data assimilation applications. As shown in this block diagram, it combines predictions from a track evolution model with PTV measurements to provide more accurate estimate of particle tracks. Yaga et al. 1993 was one of the first work that converted the filter to a particle tracker. A unique feature of the Kalman approach is that it considers uncertainty estimates at each point measurement, which means that an uncertainty estimate needs to be known a priori. Previous works estimated this based on global noise statistics. However, the recent PTV uncertainty estimation model proposed by Bhattacharya et al. 2020 provides a systematic approach to estimate the particle position reconstruction uncertainty. Hence, in this study, we seek to investigate the uncertainty-informed approach to particle tracking through the Kalman tracker algorithm, which is now informed by the recent 3D PTV uncertainty estimation model. Now, let's look at the working of a Kalman filter before we get into the details of the Kalman tracker. As mentioned previously, Kalman trackers act as data assimilation models. Given a complete track represented by the sequence of reconstructed positions yi's and its associated uncertainty ri, the Kalman filter combines it with the model predictions to give an improved state estimate xi and associated uncertainty pi. At each iteration step, the model inputs are first used to obtain the model estimate, following which the prediction is combined with the measurement to obtain a state estimate. This state estimate then acts as the input to the model in the next iteration, and these iterations continue until the Kalman estimates for the whole track are obtained. With the framework of the Kalman filter now set, let's see how this filtering algorithm is adapted to tackle the PTV tracking problem. We start with a particle at time instant k-1. Kalman's physical model would predict the position of the particle at time instant k, represented by the red cross mark. Next, we define a search radius and build a search region around the prediction, the radius value being estimated based on average particle distance in the volume and uncertainty in the prediction, given by pkp. The kth frame particles within the search region now become the candidates for pairing. For each candidate particle, the Kalman filter algorithm would combine the model prediction and the candidate's position and uncertainty to obtain an estimate for each candidate. Following this, a multiparametric tracking scheme is employed to find the best match among the candidates. Here, we also include the candidate's position uncertainty along with the standard parameters such as proximity distance, particle intensity, and shape in the pairing step. In essence, Kalman's model prediction helps identify candidate particles, and the best match amongst them is identified based on an uncertainty-informed multiparametric pairing step. Note that the proposed methodology performs pairwise tracking on time-resolved datasets. It enforces the temporal continuity similar to Shake the Box through the track evolution model. The multiparametric tracking achieves pairwise particle mapping across time frames, which is similar to 3D PTV. So in a way, the Kalman tracker can be viewed as a hybrid tracking approach. However, it also accounts for the instantaneous PTV measurement uncertainty, unlike the other methods. The proposed algorithm is currently under development, and unfortunately, we do not have results to present at this point. The ongoing work will test the Kalman tracker on a synthetic vortex ring dataset generated at 3 different noise levels. The metric of comparison will be the root mean square error in the particle position tracks. To conclude, Kalman tracker is an uncertainty-informed approach to volumetric PTV tracking. Unlike before, reliable uncertainty estimates for the Kalman tracker algorithm can now be computed from the uncertainty estimation model introduced by Bhattacharya et al. For volumetric PTV. The proposed tracker methodology performs pairwise tracking on time-resolved data, making it a hybrid approach between 3D PTV and Shake the Box. The proposed methodology is currently under development. The performance studies on synthetic data sets generated at different noise levels would be the first step in investigating the sensitivity of the tracking results to measurement uncertainty. With this, I conclude my presentation. Thank you for your interest in our work.